All right. I think we can get started. Before we start, I just want you to let you know that I wanted to let you know this webinar is being recorded. You can put some questions in the chat, so you can direct them. You can place them either publicly, or you can send a message only to me. Just make sure that at the end of the webinar, or if it's a question that can be answered in between, I'll make sure to answer your question and repeat it. So there will be plenty of time for questions as well. So I would just like to give the floor to Paul for a minute or two to introduce Electrorent, and then we can get started.
Thank you, Anouk. Hi, everyone. I'm Paul Jackson. I'm an RF applications engineer at Electrorent, and I want to thank you all today for joining us here for today's webinar on testing of aerospace and defense passive sensors and radars by my colleagues here at Antennex. And so just to give you a little bit more about what Electrorent is all about, we've been in the rental business for 60 years, and we have the largest testing and technology services. We are the largest provider in the world. The company maintains over $1 billion in inventory, comprising more than 95,000 units from over 2,000 manufacturers. Electrorent offers more than 11,000 product types and 7,000 models. So what does this scale mean for you? It means access to an extensive selection of test solutions to support your specific requirements. With 20 locations and the ability to deliver more than in 100 countries, Electrorent serves as a single source provider for both rental and purchases of any test equipment. In addition to that, of course, in Electrorent, you also get applications engineering support with any rental or purchase as well. And I will turn it back over to the team at Antennex, and thank you for your time.
Great, thank you so much, Paul, for that introduction. Let me see if I can take control of the slides again. Let's see if it's working now. Sorry about that. I'm guessing all of you can see the slides now, but if not, please let me know in the chat, and I'll fix it. So today I'm going to just give you a presentation of about half an hour, so about 30 slides. What I'm going to show to you is some background on passive sensing and radars, and especially design considerations for both of those types of systems in the context of phased arrays, and as well as what metrics are important to characterize them and test them. I'm also going to tell a little bit about how antennas we are using today are changing in terms of the topologies. And then I'm also going to introduce reverberation chambers with some test examples, and conclude it also with giving some background on the company Antennex. So my name is Anouk. I am the CEO and co-founder of Antennex, and my background is in metrology for specifically integrated antennas, so to test metrics that are relevant for antennas in RF electronics when they are an integrated system, such as in a phased array. So I'd like to start by just giving a very high-level overview of some passive sensors and radars. So, of course, passive RF sensors are used to monitor RF signals that are in the area, that are emitted by either communication systems, other radars, or just devices that are around it. So it's really important for these systems is that they have a high dynamic range, and that they can test signals that have a very low magnitude, very low power. So we need to have a very high level of sensitivity in these systems. We also want wideband operation, because we need to be able to detect signals from a very wide range of frequencies. And also what's important is that these systems are supposed to be passive, so they should not radiate, and they should not necessarily be detectable. So if we're looking at those three parts, and we're looking specifically at dynamic range and looking at what metrics are important, then these would be some that are very relevant. So I'm really focusing on hardware only here, and also I'm just focusing on a few specific parts. So there's definitely more that's interesting, and if you have questions about that in the chat, feel free to just drop that. But these are some very critical aspects and metrics that are used for characterization of them. So again, if we want to have a high dynamic range, we need to reduce loss and noise and increase gain as much as possible. So we're looking at things like antenna efficiency or system efficiency, system gain, and also aspects such as noise figure. If we're looking at wideband operation, we also need to be sure that the multiple bands and the multiple circuits we are having to enable different frequencies to work does not have too much internal leakage or interference. So we need to consider coexistence of multiple bands, but also intermods if multiple signals are coming in at the same time. We need to be able to distinguish those. And finally, in terms of detectability, we want to look at radiated emissions, spurious emissions, harmonics that might get radiated, or effects like that. And if we just only look at two simple metrics, just to give you a bit of an idea of how critical these metrics really are for the performance of your sensor, there's a quick illustration here to visualize that to you. So here we have a passive sensor placed on a map, so you can basically see a little bit of the sizes here. On the top left corner, we have a sensor with a noise figure of 3 dB and an efficiency of 90%. With everything the same, we have 4 other cases where we vary the noise figure and the efficiency. So in the top left corner, we had 25 kilometers. However, if we reduce the efficiency or increase noise figure, we can see that our system performance deteriorates pretty quickly. So that's something to really take into account here. And especially if we're talking about metrics such as antenna efficiency that are really difficult to measure well, or to measure within the uncertainty of a dB, then you can see that it's pretty significant to know that precisely and to optimize that. Similar things hold for noise figure. That's also really difficult to test. I'll get back to that as well, and very difficult to characterize accurately when an antenna is there. And it's really important to know that the antenna has a big impact on the noise figure. So this is just to give you a little bit of an idea of how these metrics impact performance. And there's, of course, many more effects that are happening that impact range and performance. Then if we're looking at radar from a similar perspective, now we are not looking anymore at RX only systems. We are really looking at TX and RX systems. So how it works is we have a detection system. It transmits a wave that gets reflected off and is received again. So we correlate the transmitted output and the received input, so we can localize devices such as UAVs, aircrafts, or other aspects that are near the radar that are critical to detect for safety reasons. So what's really important for hardware design is, besides also having a very good RX chain, is again that we have a very high dynamic range also on the TX chain. So we want to have really high output powers, but have a good waveform in the output power. We also need to have a very high isolation between TX and RX, so it's really difficult to work with such high-powered signals, but also such a deep sensitivity on the RX side. And we also want to use clean waveforms, like I mentioned before. And again, detectability is also a point. Like, these systems are supposed to radiate, but they are really not supposed to radiate everywhere. So if we're looking at metrics that, in addition to what I already mentioned, are important, are really compression of power amplifiers, because we are using very high output powers, which can compress the power amplifiers. So we're looking at effects such as nonlinear distortions that are happening here. We're also looking again at leakage from TX to RX, either internal or through mutual coupling through the antennas. So that's not only antenna isolation, it's also other types of isolations that are happening already before or after the antenna. But also things like that could potentially compress LNAs or distort LNA behavior from the direct coupling that we are having. For when we're looking at waveforms, we want to look at chirps for FMCW radars. We want to look at pulses for pulsed radars, and we also want to look at effects such as pulse droop and seeing how the magnitude may, the radiated power may get lower for certain settings and for certain effects. So for both of these cases, but also for many other applications, think of SATCOM, automotive, or communications, that's also where all these things are happening, is that the antennas that we are designing are different from what they sort of used to be. So we're using more and more higher frequencies. This is, of course, a story that you probably hear a lot, but that comes with a lot of challenges, especially in RF electronics and antenna integration. That's a lot higher now, so more integration, and we're having much more antennas. So we're having phased arrays with thousands of antennas. We are now manufacturing them in different ways, so it's no longer manufacturing a separate amplifier, manufacturing a separate antenna, and clicking that together at a later time with an isolator in between them. Now we are really having the antenna directly connected to PA output ports or LNA input ports. We're also not manufacturing them as full arrays sometimes, but we are more manufacturing them possibly as submodules. And something that we're seeing as well is that it's really not separate antennas and separate, that's sold as separate antennas and separate RF modules and front ends. It's really that companies are now selling submodules of arrays that are then later clicked into a larger array. So that's like a lot of changes that are happening here. So for your design, it's really important to know that the presence of the antenna really does change your behavior. The result that you get is not just a cascaded result of your amplifier and your antenna. It's really different when they are linked together. So here is a result where you can see that, where you can see what the effect is on the power added efficiency of a phased array when we start beamforming and when we start loading our power amplifiers. So here we can see at two frequencies, there was some beam steering in the E plane and in the H plane at 29 gigahertz and 31 gigahertz, and where we see that we have reductions over 10% in power added efficiency just because of differences in PA loading over beamforming settings. So what we're seeing is that we're really having a scan-dependent performance due to differences in mutual coupling, differences in PA loading. If we're looking at receivers, backwards noise waves can also get reflected off the antenna and then increase the level of noise in your system. We're looking at internal RF leakage and also antenna sensitivity to the environment. And by that, I mean both the antenna noise temperature and other things that it may see that are in the environment that change the behavior of your system. So that's why when we go to testing, you really need a test over the air, because the conducted world is really not the same as the over the air world. But also in some cases, it's just really not possible to test it separately because it's so integrated. So some challenges that we are seeing is that we need to get higher speeds. We're having test cases that are maybe orders of magnitude more than what we saw before. So just think of the number of beam steering settings and number of patterns that people are testing that has gone up by a lot. We're needing to do more metrics over the air. Noise figure is a very important example of that. And devices under test, we don't always have access to the RF ports or even IF ports. Oftentimes, we're just having bits to waves or waves to bits and really characterizing the full system. So a lot's changing, but especially our workflow in testing and doing more and more stuff over the air, including submodule versus full array testing. That's very different, where we see the worlds of the antennas and the RFICs coming together. So typically, people were using anechoic chambers for most of the over-the-air tests. That's, I think, something that everybody here in the call is very familiar with. But just to reiterate, the anechoic chamber is really good at looking at things that deviate over space. So it only looks at one angle at a time, so it's able to discriminate behavior per angle. By mechanically scanning around a device or by moving a device under test around. So things like radiation pattern, directivity, or polarization are really great to measure in anechoic chambers. However, there's a lot of stuff, also a lot of downsides that I think you will recognize. And this may be a bold statement, but if we're looking at phased arrays and the number of test cases they have and the levels of accuracy that they require for certain levels of measurements, anechoic chambers are not good enough by itself, and they cannot solve all of the problems that you see. So they can still solve some of your problems, but really a lot of problems they're just not able to solve. So they're not very well suited for power-based tests. And by that, I mean tests that depend on overall radiated or received power per frequency or ratios thereof. So things such as noise figures, things such as total radiated power, harmonics, or efficiency. Calibration is very complex. We're often dealing with long cables. We need to calibrate out free space path loss if we want to have any idea of an absolute power. And we need to have very good reference antennas that are well defined. So that's definitely a complex procedure that, yeah, possibly some of you also have gone through, especially in terms of setup. It's slow in both setup and test. It's very sensitive to alignment errors, especially if we go up higher in frequencies or we are dealing with big phased array antennas where the phase center is very poorly defined, and even that definition is a bit loosely defined. So there's just a lot of problems that can happen there, and also the effect of moving a device under test or probes could create some issues. You may need to design a specific holder or things like that. So those are just some downsides of anechoic chambers that I think many of you are familiar with. So they're really good at certain parts, but when we go to these complex systems that rely on a lot of power-based tests, we're really starting to see the limitations of the anechoic chamber. So this is where a reverberation chamber comes in. So these are chambers that we work on and with our company Antennex, but luckily there's a lot of other people in the world that are also working on researching and commercializing this technology so that it's more and more used across the world for antenna testing. So it's the way it works is that it's sort of the dual of an anechoic chamber. So we don't have absorbing walls such as an anechoic chamber has, but we have fully reflective walls. So where an anechoic chamber scans around the device under test and then integrates overall at the space to get radiated power, here we fix the reference antenna and we only change the electromagnetic environment by spinning around these shapes that you see in the chamber in the back right and the top left. So that's equivalent. There's both an integrating operation. However, this is significantly faster and more accurate. So in the picture, you can see an antenna under test. That's a radar. And you can see that the reference antenna is also here fixed on the side. So that it's a little golden open-ended waveguide that you see on the right-hand side. So it really acts as an integrating sphere for both transmitters and receivers. What you get with that is significantly faster tests. You can do a TRP measurements in seconds instead of hours, especially for high directivity antennas where you need to do very dense sampling in an anechoic chamber. Here you don't need to do that. There's no mechanical scanning or alignment needed, or antenna alignment needed, so we can just place the antenna anywhere we want in the chamber because we are changing the environment around it instead of scanning a probe around it. So that's really useful. You can just place a device inside, close the doors, and do a measurement that's really accurate every time. Also, you don't need to be in far field conditions. That's really something that's needed in an anechoic chamber. It's also why they're so big. So these systems can have a significantly smaller form factor. Of course, you do need to take into account that your device under test fits and that it is not like directly next to a wall, so you're not in the reactive near field. And these chambers have a very high user-to-user and lab-to-lab repeatability, just because it doesn't have all those calibration steps that an anechoic chamber has. So it's really well suited for tests such as efficiency. Here are some performance metrics to see how fast it can be and what the levels of uncertainty are. This is over a pretty wide band, a few gigahertz. We can do within 30 seconds antenna efficiency or system efficiency. We can do noise figure. We can do things that relate to total received or radiated power and power spectral density. And from there, you can get things that's linearity, compression, gain, nonlinear distortions, and I will be showing all of that. So if we look at a comparison between anechoic chambers and reverberation chambers, this is a pretty nice overview where we see that anechoic chambers are really good at tests such as radiation patterns and directivity. Reverbs, I say not at this time because technically it is possible, but from the side of antennex, that's not something we offer now. However, if we're looking at all power-based metrics and everything that relates to the performance of your electronics, the reverb is significantly better, accurate, faster than the anechoic chamber. So for most of those metrics, to do that in an anechoic chamber, we need to do a very fine spatial scan, which is not always possible for all test cases. But there's two cases, or specifically spurious, harmonics, out-of-band emissions, that you have a very high chance of missing. So let's say we have something that only comes up every couple of seconds, or yeah, it's basically not always there. We might just miss it when we're scanning around it. Something else that's important is that some effects only pop up if you're working with very high powers, and you might not be able to keep your device under test in that mode for that long to do a full spatial scan. So that's also something you solve with the reverb, because there you can test it within a very short time. So yeah, both time varying and out of band emissions are more easy to test in the reverb. I also want to mention noise figure, because in an anechoic chamber, you can definitely do G over T, but that has quite a lot of assumptions. So yeah, only if you know very well the antenna efficiency and have a very well-defined channel, you can get an accurate estimate of that in an anechoic chamber. But in the reverb, you can get a clean noise figure, and I'll get back to that. So if we go back to that figure that I showed you before, or that little list, there's a couple of metrics that I've made bold here, and that I will just show you one by one and show you how they work and how you can measure them in reverberation chambers. So the first one is noise figure. Here we see a picture of an antenna placed in a reverberation chamber, where our antenna under test, or our device under test, is an antenna connected to a low noise amplifier. We took this device because we could take them apart to be able to get a reference. But yeah, the idea is really that you are testing fully integrated antennas in this reverberation chamber. So in the setup, we have one antenna that is behind this blocking plate. That's a reference antenna, and you cannot see it in this picture. And then here we have the receiver antenna that's connected with a cable to, in this case, a PNAX with noise receiver. So the nice thing about this setup is that we only need to calibrate the cables. We don't need to calibrate the chamber. And we can do both a gain and noise figure setup with a measurement with the same setup. So we first do a S21 measurement, and from there we get the gain. And then after that, we use the reverberation chamber as a wireless noise source. We're using a cold source measurement, so the chamber is a very well-defined noise source. And from there, knowing the gain, knowing the noise source, we can get noise figure. Test time is about 1 minute for 1 gigahertz of bandwidth. And again, no antenna alignment needed. We can just place it inside, and no chamber calibration needed. Here's another example where we tested the noise figure of an integrated antenna. So this was 6 elements, and on the right-hand side, we can see the variation over both gain and noise figure per element. So each element had an antenna with an LNA behind it, and then later a combiner, but here we could measure them separately. You can see the average, or so the mean over all of these antennas, in blue in terms of gain, and red in terms of noise figure. And you can see that in the gray stripes, you can see the individual elements, and you can also see that they vary a little bit. I will say that those results were very repeatable, so this is actually the variation of the antenna that we're seeing. You can do different elements, beamforming settings, gain settings, and yeah, add things like radomes or different substrates and evaluate your noise figure in that way. Then antenna efficiency is another one that's important that I mentioned also before in the example, what you can perfectly measure in a reverb. So the only thing we need to do for a passive antenna is just do an S11 measurement where we only calibrate the antenna, or sorry, only calibrate the cable. We place the antenna inside the chamber, and then the method takes care of the rest. You can get total efficiency, radiation efficiency, mismatch, and for active antennas, we can do an S21, and you get return loss and system gain. So again, no antenna alignment needed. The test time is only a few minutes for several gigahertz of bandwidth with a low uncertainty. So this works with a VNA. Here you can see some results as well, taken from a phased array, where we were looking element by element at what was happening. So just imagine that you're in your design cycle of your radar or any phased array, and you just want to see what the variation is per element. You want to verify in R&D if all of them work before you start integrating everything and before you head over to the next steps. That's what you can do here. So whether there's LNAs or PAs behind those antennas or whether it's fully passive, you'll be able to use this method and see what happens for different packages, for different materials or radomes. You can see the effect on efficiency. And then also, if we're looking at emissions, so the previous two methods, they work with the chamber in collaboration with a VNA, where for noise figure you needed a noise receiver. But if we want to look at the emissions, that of course we want to avoid as much as possible for passive sensors, then we need to use a spectrum analyzer. So all very similar as in a conducted way. So here's a small example of something that was not supposed to radiate at a certain frequency band, but did. There was a small consumer drone that had a video link at 5.8 gigahertz. So it was really not supposed to emit anything above 8 gigahertz. And here in the plot, you can see on the x-axis 8 to 20 gigahertz, and on the y-axis the spectrum that we're seeing. So configuring the whole setup and setting everything up was less than 5 minutes, and really, setting up the drone in place, closing the door, and doing the full test was in total less than 1 minute for this entire band. So you can see how incredibly fast it is and how incredibly fast you can iterate over different settings, over different beamforming settings, gain settings, and see exactly what's happening and what's being radiated. Now in an anechoic chamber, you would need to do a full scan for possibly every frequency or do a full sweep at every position and do that for every scan. So getting these tests done accurately can take you really several days or maybe even weeks, depending on the number of settings you want to test. So what we're seeing here is really the total radiated power for each frequency over this frequency band. So we've really integrated across the drone, so we see exactly what's been radiated. Then I've shown you antenna efficiency, noise figure, system gain, and spurious emissions. And then I also want to show you effects such as intermods, interference, some coexistence effects. There's, of course, many effects that can happen, but I just want to highlight specifically one measurement that we've done on an antenna package. We've also wrote a blog post on it on our website if you're interested in seeing that. So here we had a 100 gigahertz antenna package. We saw effects both in RX and TX that were related to the local oscillator. So the only thing that we saw in an anechoic chamber, which is where we initially started to test this phased array device, we only saw that we had changes in DC current and that we had changes in a measured RF amplitude. So we were not entirely sure what the effect was. But in the end, we found that there was some internal leakage in the system of the LO, which caused the LO to move to different frequencies when we had it set to different power levels. And that's what you see here. And that's what you see here in the figure. So you see on the x-axis frequency, so you can see 96 gigahertz. On the y-axis, the power spectral density. And then each different color is a different LO power. So the only thing that should have happened is that the magnitude goes down, but we're also seeing it shifting over frequency. These are the types of effects that you'll be able to see very well in reverberation chambers, and again, not so well in anechoic chambers. Then on top of some of the things that I just mentioned about passive sensing, there are some additional things that are important for radar, because we do have now also a TX channel. So I'm going to show you some things about compression characteristics, so nonlinearities. Again, leakage and coupling is important, and LNA compression as well. If the isolation is maybe not so good, or the reflected signal is high, as well as waveform detection, such as chirp, pulse, rate length, and pulse droop. Now, what's something that's also good to mention before I show the metrics is that if we're looking at highly directive systems, we should realize that not always the power goes into the direction that we fully expect. So let me just explain that to you a little bit with the left figure. Here we see a simulation of a 16-element array just in 2D, where you can see the radiation pattern normalized. So this was simply a simulation. Now just realize the bandwidths that we are using for those phased arrays. We might get some beam squint. So within it might be that at the lower end of the frequency that we're using in, let's say, an FMCW signal, we might be a little bit to one direction, and it moves a little bit while it goes to higher frequencies in the FMCW chirp. Then if we're only looking at one direction and we're only measuring at one direction, such as in an anechoic chamber, we might not see very well where that difference in magnitude comes from. So that's one of the effects that is happening. Something else that's happening that goes into that can give you much larger errors is spurious emissions and harmonics. If we look at this red pattern that we're seeing here, that would be the harmonics of this array. So because they work in a different frequency, they also beamform in a different way and in a different direction. So to be able to characterize this well in an anechoic chamber, you will need to do extremely fine scans for every beamforming setting to get that. It's not only harmonics, it's also nonlinear distortions. Here's a nice illustration from a paper that I took. Here's the reference, where we can see that the nonlinearities also beamform in a different way. So the only thing that beamforms as you designed it or as you expected it is the carrier, but all the other unwanted effects might just beamform in a completely different direction. So if we're checking adjacent channel leakage ratio over space, we can see very large differences there, and we might miss certain effects. Now, that may be also something that you in the end want to check to see what's happening per direction. Again, that's really great in anechoic chamber, so that's how both of the systems are very complementary. But to see first if they are there and what the magnitude is, and really to characterize your system as you would also do in a conductive way, as you're used to, there the reverberation chamber can get you pretty good answers. So yeah, let's start a little bit with nonlinear distortions and characterizing under realistic waveforms or wideband signal conditions. What we've done here is we have excited an amplifier, a power amplifier and an antenna with a specific signal, where we were using a wideband condition, created with a multitone signal with a vector signal generator. We see on the x-axis again the frequency, and on the y-axis we see in this case normalized power, but we can also get you the absolute power, so you can get total radiated power. And if we leave a gap in the middle, we can get things like noise power ratio, but by evaluating the full spectrum, we can see, of course, harmonics, adjacent channel leakage ratio, and effects like that. Here we see that for increasing powers of the amplifier with the antenna, we also see increases in in-band and out-of-band distortion. So that's how we do it with the gap in the middle, and you will already be able to get quite some information on your device under test. Later this year, in June at IMS, we are going to release an upgraded version of this, where we can really see the distinction between in-band and out-of-band nonlinear distortions, and distinguish that from the excitation, and distinguish that as well from noise. So we can do that under realistic signal conditions, either continuous wave in a test mode, or in wideband conditions. And this is an example of a result that you would get out of the reverberation chamber. So here's normalized frequency, and on the y-axis, that's radiated power. Then, besides just checking the hardware, seeing what happens in compression, seeing what are the nonlinearities in your array, we can also check the waveforms themselves. And here are some examples for FMCW radars. So we've tested a 60 gigahertz Texas Instrument radar. The setup was the one that you are seeing right here. And the result that you get out of it is, this FMCW, famous spectrogram of a chirp. So we can see time, we can see frequency, we can also zoom in over what's happening over frequency. So we can evaluate our hardware, and things like antenna mismatch are taken into account. We can do TRP in less than a second with pretty low uncertainty, and evaluate effects such as chirp linearity, chirp rate, length, power spectral density, and harmonics. And this setup works together with the oscilloscope. It's not only FMCW that we can test, we can also look at pulsed radars. So we can see the over-the-air behavior of the pulses in when it has different rates. We can really zoom in as what you're seeing there at an instance in time, and to see the behavior over frequency there. So you're really able to isolate what your device is doing in both time and frequency effects. And depending on your setup, you can also look at very specific effects on the pulse, such as pulse droop, or looking what's happening really at a certain moment instance in time. So that's mostly some of the things that I wanted to show you. I've mostly given you a high-level overview, but if you want to know more in depth how some of the methods work, and what other use cases we've done, you can always reach out to us, and we can set up a more specific meeting to talk about that, technical discussions. It's important to know that Antennex does several things. So we offer custom hardware, software, but also services and consultancy. So we sell chambers. There are chambers that have software included, that have compatibility with well-known OEMs fully included. And we also have installation and training and things with that. And finally, our software-only solutions also work with existing reverberation chambers. So you might already have a chamber. We can talk with you about that, see what brand you have, and see how we can run the Antennex software on your existing chambers. And if you just want to try it out, try the technology out, or you have something to measure that you couldn't measure right now in the anechoic chamber, but you would like it tested in our chambers, we can do that too. Finally, also about Antennex is we don't support only R&D testing. We also support low-rate initial production testing and end-of-line tests. The chambers and the methods, as I've presented to you today, are used for radar production tests. Think of subarrays. And we're also able to make custom solutions if needed. Future releases are larger chambers. We're also going to include ERP, and EVM is something that we are going to release at June at IMS in this year. Other applications that you might think of for these types of chambers are material characterization, effects such as absorption cross-section, so the absorbing part of radar cross-section, and also jamming and immunity testing. If you're interested to try it out, we are compatible with several brands, as I just mentioned. The chamber automatically recognizes that it's connected to, let's say, a Keysight VNA or spectrum analyzer, so you don't need to write Skippy commands, and everything works immediately. We have options for rental of chambers, rent to buy, lease, and purchase, options for software only, like I just said. And in the US, Electrorend is our exclusive Antennex distributor, who co-organized this webinar as well. So that's with Paul. And if you want to try it out and you want to have an on-site demo, just reach out to us and we can make sure it happens so you have the opportunity to try out the technology and see if it works for you and your lab. So in conclusion, we're seeing that the integration with antennas and RF electronics changes both design and test of these devices. So we're really changing workflows here in the design and the test part. Phased arrays require a lot of tests that cannot be served by anechoic chambers only. So we really need to look at different ways to be able to get the products on the market in time with the right reliability that we require. And using reverberation chambers has a lot of unique benefits. It's not a full replacement of anechoic chambers, but it's a very nice complement. It can take away a lot of the test for you, and it can really reduce the cost and time per test in your phased array development. And also it can do many of the tests more accurately with a higher repeatability, so you have more confidence in your results and more reliable production testing. So that's what I wanted to tell you today. Maybe there's one more slide here about connecting with Electrorent that Paul just wants to detail.
Yeah, thank you, Anouk. So as Anouk mentioned, in the US, Electrorent is the exclusive distribution partner with Antennex. Contact your local Electrorent account manager or reach out to us at electrorent.com or follow us on our LinkedIn, and we'll have posts and can help you support you on any questions you may have or any needs with the Antennex Smart Chamber. Thank you.
Great. If you have any questions, feel free to write them in the chat. I haven't seen any questions coming in yet, so I'm just going to give everybody a couple of minutes in case they have specific questions or they want to know certain things. So just feel free to ask your questions here, and I'll just repeat them and answer them.